Hi guys, it's your guy Olumde, and today we're gonna be talking about the binary search problem solving techniques. It has so many applications and it is um, commonly hacked by top tech companies including Google, Amazon, Netflix, Microsoft. In fact, every tech company will make use or we have a real-time application of the binary search problem solving techniques, be it meta in searching for users, or any banking app that is used to search for transaction histories, anything that involves searching through a wide variety of database. Definitely binary search is going to be used in solving those complex scenarios. Now let's get into the introduction. Let's say you have a standard hard copy English dictionary and you want to find the definition of the word internet. How could you do this? One way is to flinch through the book page by page, a page at a time, until we get to the letter I, and until we get to the page containing internet. But this is inefficient, and realistically we are just gonna immediately open up to a page right in the middle of the English dictionary. So let's say we just perform an open, and we open right into the middle of the dictionary, and let's say we appear at a page that is containing words that start from M, that is M pages of the dictionary. So actually we are finding the word internet, and it's to the left of M because I comes before M in the alphabet. And because of that, what we do again is that realistically we want to open to just the middle between A and M. You understand? So, and then we continue that way on and on. Probably we open to F, just like it is illustrated in this diagram here. Let's say we open to F, and then we are looking for I. We know that I is after F, so we are gonna shift. We are gonna select. We are gonna select a page again that is between F and M, and we continue that and that until we get to the I that we are looking for. So actually what we just did is an illustration of the binary search operation, whereby we are looking for a particular, because a dictionary is ordered alphabetically, and when we open right at the middle, we come to M. Because we are looking for I, we shift to the left and open right at the middle to the left between A and M, and then let's say we get to F. Then right from F, I is toward the right because F comes before I, so we shift again and we continue like that. So that way we have effectively observed the binary search technique. Binary search is basically an algorithm that searches for a value in a sorted data set. Sometimes even great engineers found it difficult to utilize binary search algorithm correctly because of certain edge values, edge cases and conditions, like how should the boundary variable left and right be initialized, where do we place them, what position do we place them, or some other thing that could cause a conflict is, should we use left is less than right, or left is less than equals to right as the exit condition of our while loop. Another one is that how should the boundary variable be updated? Should we choose left equals to mid, or left equals to mid plus 1, right equals to mid, or right equals to mid minus 1? So all of these conditions are really can really go a long way in defining our algorithm. And so some engineers are always at the middle of which particular condition to go for, or how do we initialize the boundaries of the window, because binary search also deal with a particular scope. In this video, we're going to be offering a clear guidance on how to address these challenges. To implement a binary search algorithm, the first thing we need to do is to define the search space. So search space actually consists of all possible value that could be our potential our target value that we are finding. So for example, now in a to find a target in a sorted array, so our search space will be every element in that array. The entire array will be our search space, because the target could be found anywhere within the array. And that's why we place a pointer at the two extremes of this array to signify the boundaries of our search space. So it actually encompasses every element in the array. So that's the first thing we define when implementing the binary search algorithm. The next step is to narrow the search space. Since we have defined the search space, we are going to narrow the search space, and narrowing search space actually means progressively moving the left pointer or the right pointer that signifies the boundary of the search space, progressively moving each of them or both of them inward until the search space remain one or no element at all. In narrowing the search space, we can either narrow it toward the left by shifting the right pointer inward, so it can move closer to the left. So we can see that the search space is effectively narrowed down to the left. Why? Because we have ignored some element to the right, so it has been narrowed to the left, and we can decide to narrow it to the right, so by shifting the left pointer to the right, so therefore minimizing the search space, making it more narrow by losing grip of certain elements that are at the left, because we are actually shifting the left pointer toward the right. So these are the two ways we can navigate a search space. We can narrow a search space. Now, to decide whether to narrow the search space to the left or to the right until it become one or none element in it, is actually going to be decided by the middle pointer. So the middle element is going to decide where we are going to narrow it to. And the main question to ask now, whenever we want to navigate and want to narrow a search space, is that is the value we are finding, is it toward the left of the middle number? Don't forget, or toward the right of the middle number. Don't forget, when we are trying to give the dictionary illustration, we said we are going to go, more intuitively. We want to go and select right at the middle of the dictionary book, and then depending on whether the alphabet at the middle is greater than the one we are finding. Let's take for instance M is greater than I, so we navigate to the left. So that's what I'm trying to say right here now, that based on the middle, binary search is actually optimizing the fact that the array is sorted, or the data structure is sorted. So it knows that if we are finding something is sorted, it will either fall to the left or fall to the right. Let's say that we have an array of 1 to 10 sorted. So if we are looking for 3 now, and then we go right into the middle is going to be around 5. It's going to be the fifth element in the array. So we know that definitely, because this fifth element is greater than what we are finding, the value we are going to be finding now, where we are going to be finding our search space now, is going to be to the left, meaning that everyone to the right will definitely be greater than 2. Since 5 is greater than 2 and the array is sorted, then definitely every number to the right will be greater than 2. So we only have to be concerned with the number to the left. Just like in the case of M and I, we know that if M can be greater than the value I that we are looking for, definitely everything that follows M to the right, M, N, O, P, Q to Z, are going to be greater than I. So that's exactly what we are going to be doing here. So the where we navigate and where we narrow our search space to, whether to the right or whether to the left, will be determined by the middle value. So we're going to be randomly picking the middle value now, and if the middle value is lower than the value we are looking for, definitely if it is lower than the value we are looking for, definitely the value we are looking for will be to the right of the middle value, and every value to the left of the middle value will always be lower than the value we are looking for. But if the value at the middle is greater than the value we are looking for, then definitely every value that follows the middle point to the right will always be greater. Why? Because they are sorted in ascending order. So, and that's what the binary search algorithm is leveraging. Is leveraging the fact that the array or data structure that we are dealing with is sorted. Now that we understand why we are going to decide to narrow to the left by shifting the left to the right, or narrow to the right by shifting the left to the right, or narrow to the left by shifting the right to the left. Now let's see how we can narrow to the right. There are two ways we can narrow the search space to the right now. So definitely narrowing the search space to the right actually means shifting the left pointer toward the right, so that it's going to be narrow toward the right. So but there are still two ways to do that. Is either we set the left pointer to the middle value plus 1. Why? Because based on this middle value, it tells us that okay, the value you are looking for, the target is toward the right, so we have to narrow to the right, and we can do that by placing the left pointer to and setting it to middle plus 1, meaning that just the particular value that is next to the middle position is where we are going to narrow our left pointer to and our search space to. You understand? We can do that, and we can decide to set the left pointer to mid. So setting the left pointer to mid, we are just going to narrow it by placing the left pointer at exactly that middle value. So both of them actually have how we do it. So it's actually a confusing something, but it is not as complex as people might think. So we use left equals to mid plus 1 whenever we are sure that the middle value is definitely not what we are looking for. Okay, let's say we are looking for 3 in an array of 1 to 10, and then we go for the middle number now, and the middle number is 5. Fine, 3 is less than 5. We have to narrow to the left because the value target 3 that we are looking for is toward the left. Why? Because the middle value is 5, and because it is ordered, every value that follow that middle value is gonna be greater than or equals to 5. So we have to set our right pointer to the middle value plus minus 1. Why I say that we have to set it to, well, there are two things we can do there, just like we have it here. Either setting our right pointer to middle value exactly, that way we have narrowed it, or we can set it to middle value minus 1. But we are going to set it to middle value minus 1 because middle value is 5. 3 is less than 5. 3 is not equals to 5. So it's not necessary to pick 5 to be within our search space. You understand? So there is no need. When 3 is not equals to 5, definitely we can just set the right pointer to mid minus 1, that is that position minus 1. So why? Because we are sure that 5 is not equals to 3. So but in a situation whereby that middle position can be a potential target, we are going to say left equals to mid or right equals to mid. So that's the two way we can navigate to the left and to the right. So when we're navigating to the left, like I said, we are going to be effectively shifting our right pointer based on the middle position, or based on the element at the middle position. So if the element could be a potential target to a potential answer or solution, we are going to be setting the right exactly at mid, so as to include that element in the search space. But in a situation whereby it is not a potential, it is so obvious that it is not a potential solution, then we can just set our right to mid minus 1, so that it could extract mid alongside. It's gonna remove mid from the search space along with every other element that follows mid. Alright, we are going to be talking now about how to calculate the midpoint. So we are still on the second step, which is the narrow the search space. So we talked about the first step that involves dividing the search space, which in most cases is by considering the entire array or data structure, because there could be the potential targets we are looking for. So the second one is to narrow the search space, and we talked about that now. So and the continuation of it is that we need to calculate the middle point. How do we get the middle point? Fine, we've defined the left pointer and the right pointer that actually specify the search space or the boundaries of the window of the binary search space. You understand? So how do we get in touch with this middle pointer? So we can calculate the middle pointer by just finding, this is Python definition now, just taking left and right, adding them together and finding the normal median. So why we are putting these two quotations is that it performs the quotient division, so whereby it will not give us a decimal or a point. It won't give us points, so it's going to give us a whole number. Don't forget that we are dealing with sequence, or let me say we are dealing with data structure. So, and if we want to index, there must not be point there. Imagine indexing 2.2. So no, we have to index 2. So in a situation whereby let me say in a situation whereby the array is an array of 1, 2, 3, 4, and 5. Imagine now, so here now we are going to set our left pointer to 0, right? We are going to set our right pointer to what? So to 0, 1, 2, 3, 4. 4. You might be wondering why not 5. Well, we used to we deal with index based positioning. So we can't position it to 5. Why? Because if we position it to 5 now, you know that 5 is out of index here, and the right pointer must be at the at the extreme, or well, it might not be at the extreme, but it must not pass the length of the array, or else it's going to give us an index error. So we are going to set it to 4, and in this situation now our middle position will be 0 plus 4 divided by 2, that is 2. So 3 will be our middle position, although the middle position is going to be a pointer that is pointing at the index 2, and if you look at the index 2 here, it corresponds to the element 3. So that's how to effectively calculate the midpoint. Now the third step in implementing a binary search algorithm is to choose an exit condition. So choosing an exit condition can be quite tricky because you don't know which one to go for, whether left is less than right or left is less than equals to right. You might be wondering, why do you have to use left is less than right? Fine, right here we talk about dividing the search space now, which most likely and generally will encompass the whole of the data structure. So, and then we talked about narrowing the search space by moving the left and the right pointer inward. You understand? So that's literally how we narrow the search space, right? So now if we want to exit the condition, we see that whether we are narrowing the left pointer inward, narrowing to the right, or narrowing to the left, or doing both of them at the same time, definitely we need to exit the algorithm. We need to exit the loop, and then the point at which we are going to exit the loop is whether it's either when left is less than right or when left is less than equals to right. Why we say that is because, see, in this case now, left is at the extreme now, and we know that left is going to approach right, or right is going to approach left, or both of them are going to approach each other. So there's definitely going to be a point whereby both of them will meet. So at that point is when we say that left is less than or equals to right. So that way we know for sure that left is less than right. Why? Because left is at this far extreme now, at the first position, while right is at the last position, right? So we know left is less than right. So but in a situation whereby left becomes greater than right, there's gonna be a problem. You understand? So the two conditions that we hold, or the two conditions that must satisfy before the loop continue, is that the left must be less than right, and left must be less than or equals to right. You understand? So why we have this one actually strictly is based on left being less than right, in such a way that whenever the left and the right eventually meet each other, definitely we need to exit the loop. While the other one means that fine, we tolerate left being equals to right, they can meet, but they must not, right must not become smaller than left, or left being smaller than right. What I'm trying to say is this: in this particular case now, the condition while left is less than right means that the whole loop should keep going and should keep flowing as much or as far as left is less than right, not equals to right. So whenever left and right meet, it's going to exit the loop. Just like in this situation now, it's going to exit the loop. That's what left is less than right means. Now you see this one that is here that says that left, while left is less than equals to right, we tolerate left and right meeting, it will still continue the loop. But the moment right move toward the left and left adjust toward the right, such that left is now greater than right, they are no more equal, left is now greater than right, is gonna cut out of the loop. And so there are different scenarios whereby we use both of them. You will understand because here is actually an introduction to binary search to get you familiar with the algorithm, while we are going to be going in depth by considering different problems so that is associated with the binary search algorithm. So we are going to be testing the different cases whereby left is less than right and whereby left is less than or equals to right. But I think right now you can understand what it means for left to be less than right. So the moment they meet, we cut out of the loop. So it is mostly used and mostly common when we want to get that particular value at which they meet. So you understand, when the goal is that they meet. So once they meet, we exit the loop and we have what we want to have. Why this one now is actually is just another scenario whereby even if they meet, we still want to go on with the loop. So we're going to be considering both two scenarios in the coming videos. So, and then the fourth step is to return the value, because we definitely would have exit the loop. At that point we then return the value. So, and this is just one of the scenario whereby this is the while left is less than right scenario, so that whereby once left becomes equals to right, once they point at the same elements we return. So in most cases we use this condition when we want to make use of this particular element whereby they meet. So we are going to return that correct value. The time complexity of binary search is 0 log n, or O log, is actually O log n, not 0 log n, O of log n, where n is the number of values in the search space. So you might be wondering why is the algorithm logarithmic. So it's logarithmic, and why this is because in each iteration of the algorithm it divides the search space into half until a single value is located. So it keep on dividing it instead of iterating through it linearly. It actually divides it. So if we have n numbers now, for just one loop, for just one single iteration, it's gonna divide it into n over 2. Imagine now, and then when we want to perform the second loop, it's still gonna divide it again and continuously dividing it into half until there's just one left. Now, a reward application of the binary search algorithm is in finding transaction search in financial systems, so like banking apps now. So it's used to figure out financial transactions. So we see that in financial system, the binary search can be used to quickly find the transaction or record by narrowing down the search range, as the data is typically sorted in order. So it can be sorted chronologically, it can be sorted by dates or by any other factors. So, and it's gonna help us to search for a record in that transaction records. So this make it efficient to retrieve specific entries without searching through the entire database. Don't forget how the binary search work is just gonna divide it into half for each iteration. So that's it. And also it can also be used for probably profile lookups. Okay, you go to your Facebook now and Meta now, and you wanna search for your friend. So there are thousands and millions of users. There are millions of users in the database, or probably they might have some redundant database. Fine, they can have other means of creating an efficiency by having multiple database across multiple data center. But still, binary search is gonna help make the job done faster by making it easy to retrieve usernames and data across the database. So we are going to be talking about a lot of we're going to be solving a lot of binary search problems that involve binary search techniques. So including find the index, including find the target in a rotated sorted array, this and different questions and like that. They are upcoming. I'm gonna be dropping them, so don't forget to like, comment and share, and tidy up for the next upcoming video. Thank you.